Okay, let's dive into this. Welcome to today's Explainer. We're going on a fascinating journey into the literal, physical pathways that actually make network communication possible. We spend so much time talking about software, protocols, and the cloud, it's kind of easy to forget that at the end of the day, the internet is intensely physical. We're going to unravel the cables, the connectors, and the incredibly clever engineering sitting right inside your walls.
So how does data actually travel from the wall to your computer? It's a question we almost take for granted today, right? How exactly do those invisible electrical signals physically travel from a central router all the way through a building's labyrinth and into a PC without degrading or just getting completely lost in the noise? Well, to figure that out, we've got to look at the very foundation of networking. Starting at the macro level, we're looking at transmission media. Now, I know it sounds a bit academic, but these are literally just the physical paths. The copper and fiber that conduct the electricity to bring your local area network to life. Whether you're transferring a massive 4K video file or just sending a quick ping, these are the fundamental building blocks moving that signal from point A to point B.
Let's see how this builds into our first major category, unshielded twisted pair, or UTP. The design here is remarkably simple, but honestly, it's brilliant. We're looking at two 22 to 26 gauge copper wires twisted around each other. But why the twist? Well, twisting those copper wires physically reduces crosstalk and signal emissions. It's just a really elegant engineering solution to keep that data stream crystal clean.
It's fascinating to see how these twisted pairs are actually standardized to handle different speeds. You can see how the capabilities scale up. We start down at Category 3, handling basic voice and 10 megabits per second, and move up through Cat 5 and 5e for 100 to 1,000 megabits. But the real standout here is Cat 6. Cat 6 handles data signals at speeds up to 550 megahertz of bandwidth. To pull that off, it actually requires a soft supporting member right in the center of the cable to maintain its precise geometry.
All right, let's anchor these abstract specs to reality. If we trace the physical path in a typical twisted pair arrangement, it starts centrally, usually from a server and hub or switch sitting in a rack. A short patch cable connects that hub to a patch panel. Then, from the back of the patch panel, the UTP cable is hardwired, running continuously through the building until it hits a wall jack near your desk. From there, one last patch cable makes the final jump to your computer.
So the crucial point is deciding what kind of twisted pair you actually need. Unshielded twisted pair, UTP, is the standard. It's what you'll find in almost all typical office setups. But if you're running cables through an environment with high electromagnetic interference, say a factory floor with massive electric motors or heavy power lines, you absolutely need shielded twisted pair, or STP. STP uses a foil shielding specifically designed to block out that intense external noise. And this brilliantly illustrates the main alternative when twisted pair just isn't the right fit: coaxial cable. Notice the name, coaxial. It gets that name because it's a shared axis design. Right in the center, you've got a relatively stiff, solid copper wire core. That core is surrounded by an insulating dielectric foam, and then wrapped around that is your second conductor, a braided metal wire mesh, with the whole shebang finally wrapped in an outer cover. Within those coaxial networks, there are two primary sizing standards you'll run into. First up is ThinNet. Used in 50-ohm RG58 specifications, it's a flexible cable about a quarter-inch thick, which makes it incredibly easy to work with. On the flip side, we have ThickNet. Used in RG8 and RG11 specs, ThickNet is rigid, it's much bulkier at about 0.45 inches in diameter, and it features a significantly thicker copper core. When you visually lock in the internal coax structure right next to the physical footprint of ThinNet and ThickNet cables, you can really see how much more robust that ThickNet copper core is. Keep in mind, though, standard coaxial networking generally taps out at speeds of 10 megabits per second, with a maximum drive distance of 185 meters.
Okay, so now that we've covered the long runs of cable, let's zoom all the way into the micro level. How do these cables actually terminate and plug into our devices? Enter the RJ45. RJ stands for registered jack, and this specific 8-position 8-conductor jack is the absolute undisputed standard for 10 base T and 100 base T Ethernet wiring. Here's what that physical plug looks like up close, with its 8 distinct pin positions. Now, here's a fascinating fact that surprises a lot of people. Even though a standard RJ45 cable contains 4 pairs of wires, so 8 individual wires in total, standard 10 and 100 megabit Ethernet actually only uses 2 pairs. Yep, just the orange and the green pairs.
The blue and brown ones are traditionally reserved for a second Ethernet line or phone connections. Crazy, right? Because we've got 8 colored wires and 8 pins, we need a strict map for what goes where. There are 2 primary color codes for wiring, T568A and T568B. They both map out exactly which colored wire goes to which of the 8 pins. They use the exact same colors, but the only difference is how the green and orange pairs are physically swapped on pins 1, 2, 3, and 6.
Let's step out of the theory for a second and look at the hands-on process. To secure these wires into a wall plate, also known as a keystone jack, it's a 3-step process. First, you match your cable wires to the color code printed right on the jack. Second, you place the wires into their corresponding slots. And third, you use a specialized tool to literally punch down the solid copper conductors into tiny metal blades inside the keystone.
Seeing the punch-down tool in action really connects the dots. It forces those wires perfectly into the I/O box. But there's a critical limitation you have to remember here. This entire physical hardware arrangement, from the hub, across the patch panel, all the way to this wall socket, extends network connectivity up to a strict maximum distance of exactly 100 meters or 328 feet. Go any further than that and the signal degrades.
So that brings us to our final major concept. And it's a question that trips up a lot of people when they're building a cable. Straight through or crossover? How do you actually know which wiring method you're supposed to choose?
Well, the golden rule is actually beautifully simple. You use a straight-through cable when you're connecting different types of devices, specifically data terminating equipment like a PC to data communications equipment like a hub. On the other hand, you use a crossover cable when you're connecting similar devices together, so PC to PC, router to router, or hub to hub.
To see how this works physically, notice that a straight-through cable uses the exact same standard on both ends. Pin 1 goes to pin 1, transmit connects to transmit. But a crossover cable brilliantly mixes the standards. You put T568 on one end and T568B on the other. This physically swaps the transmit and receive pins across the cable, preventing 2 identical devices from shouting over each other on the exact same wire.
As we wrap up this explainer, I want to leave you with a provocative thought. We live in an era of wireless everything, right? Satellites, massive fiber optic backbones. But step into almost any office or server room on the planet, and you'll see that the entire modern internet still fundamentally relies on these delicate, colorful, brilliantly standardized, correctly twisted and punched down little copper wires. Knowing how they work is understanding the literal foundation of our digital age. But as we push towards multi-gigabit wireless and massive fiber rollouts, you really have to wonder, how much longer will copper actually rule the last 100 meters of our networks? Thanks for exploring with me today.